So we wrote down these equations. X equals x naught plus v average times time. The second equation was v equals v naught plus the acceleration times the time. Equation 3 was the definition of the average velocity. And then 4 and 5 were combinations of those equations. Which allow us to solve more complex problems without having to apply multiple equations in a row. Sometimes you can just grab one equation and answer the question where just one of these alone wouldn't work. And so these are kind of three independent equations, and these two can be obtained from these three. This comes from the definition of the average velocity. This comes from the definition of the acceleration. And this is also just a different definition of the average velocity. This was all sort of implicitly horizontal motion. We talked about bicycles and cars and people running and stuff like that. But now we're going to talk about vertical motion. And so what we're going to do here is we're going to change x to y. We're going to use y for the vertical motion, right, and x for the horizontal motion. And so we're going to send x naught to y naught, and x becomes y. And then we're going to replace v with v sub y, so that we know we're talking about the y direction. And then replace v naught with v naught y. And finally, we're going to replace the acceleration with the acceleration of gravity, which is minus 9.8 meters per second squared. And so this is just things that you drop or things that you throw. The only acceleration we'll have for our vertical motion is this, and we define g as 9.8 meters per second squared. And so a becomes minus g. Because objects accelerate when you drop them at 9.8 meters per second squared. And we'll talk about that more as we go. What I'm going to do is I'm just going to rewrite these equations for y now, for free fall. And so this equation becomes y equals y naught plus v average. And I'm going to put a little y here so that we know it's in the y direction, times time. Vy is equal to v naught y minus g times time. So I've replaced with the v's with the appropriate y versions, and the acceleration with minus g. Instead of plus a, it's minus g. That's what I have down here, right? This becomes v average y is equal to vy plus v naught y over 2. This becomes y equals y naught plus v naught y times time minus 1/2 g t squared. Right? I've replaced the a with minus g, and that looks like that. And finally, I have vy squared is equal to v naught y squared minus 2g times y minus y naught. And so these are the equations, the corresponding equations. I can number them 1, 2, 3, 4, and 5 for free fall, for vertical motion with free fall. The reason it's called free fall is because I'm not letting the acceleration be anything. I'm letting it be specifically the acceleration of gravity. And so unlike in the x's where I was letting the cars accelerate at any rate, everything is going to move according to gravity for these guys. We could plug in different values of a, but for the time being, we're just going to use free fall, what we call free fall, so objects being influenced by gravity. And so notice this was our horizontal motion, this is our vertical motion. We didn't have to go through all the process of getting there. We just replaced the variable names and recognize that the math tells us it's going to be the same. Okay. So a ball is thrown vertically. So I take a ball and I throw it vertically, right? V naught y is equal to 40 meters per second. And we're going to ask the question, what are its position and velocity every second after that? And so I'm going to make a table, and I'm going to say this is the time in seconds, this is the position in meters, and this is the velocity. I'm going to move this over a little bit. This is the time in seconds, this is the position in meters, and this is the velocity in meters per second. Right. And so I'm just going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, something like that. Right. And so it's thrown vertically, and so at t equals 0, that's the instant it leaves my hand, say, and we're going to call that its initial height is 0. Right? I'm not going to put the units in the columns because the units are all indicated at the top, right? Well, what's its initial velocity? Its initial velocity is 40 meters per second, and so we're going to say, and here I said I wasn't going to put the units in, and there I did anyway. So its initial velocity is 40, right? At t equals 0, it's just leaving your hand, which we're going to call the initial height is 0, and it's traveling at 40 meters per second. And so now the question becomes, what is its position, height, and velocity 1 second later? And so we have our equations, and so I'm just going to write down the first three. I'm going to say y is equal to y naught plus v average y times time, and I'm going to say 2 is v y is equal to v naught y minus g times time. Remember we said g is equal to 9.8 meters per second squared. But for discussions on the board and stuff, I'm just going to use g is equal to 10 meters per second squared because it's just easier to do math with it. It's only a 2% difference, so let's not panic. We're just going to assume it's 10. And so now I can say, well, how can I calculate the any of these things after 1 second? And I can look and say, well, if I know its initial velocity, which is 40, and I know the time, which is 1 second, I can calculate the final velocity. The initial velocity is 40, so I can say 40 meters per second minus 10 meters per second squared times 1 second is 30 meters per second. So I know at t equals 1 second, this is 30. Right. Now I can go grab this equation, and I can say, look, the final position is equal to the initial position plus the average velocity times the time. I know the average velocity here is 35 meters per second, so I can say y is equal to y naught plus 35 meters per second times 1 second, right? This guy is 0. We already said the initial height is 0, and so this guy just becomes 35 meters. Okay. Now I can say, well, what is its velocity after 2 seconds? Well, I can either start with its initial velocity, and I can say, look, its initial velocity was 40 meters per second minus 10 meters per second squared times 2 seconds, and get 20. Or I could have started at 30 meters per second. I could say after the first second, his initial velocity is 30 minus 10 meters per second for 1 second gives me 20 again. So I can calculate that in a couple of different ways. And then once again, I can say, well, so for this one, I can say, look, y is equal to y naught plus v average y times time. And I can say, look, that's just 0 plus, well, if I look at this 2 second interval, the average, 40 initially and 20 final, the average is 30. So it's 30 meters per second times 2 seconds, or 60 meters. Right. I could also say that starting at this point, the average velocity between this second and this second is 25, and so it traveled at an average velocity of 25 meters per second for 1 second. And so in this second, it traveled 25 meters, plus the 30 it traveled initially also gives me 60 meters. So I can either look at the whole interval, in which case it's 2 seconds with an average velocity of 30 meters per second, or I can look at this 1 second interval, in which it's 1 second at 25 meters per second, so it traveled 25 meters, plus 35 gives me 60. Okay, erase some of this over here again. And so now I get to the third one, and hopefully you're starting to see a pattern, right? 40, 30, 20. This is going to be 10, right? It's 40 meters per second minus, Vy, let me just do it right. Vy is equal to 40 meters per second minus 10 meters per second squared times 3 seconds, or 10 meters per second. You can see that every second that goes by, another 10 meters per second gets subtracted off the velocity. And so if we wanted to, we could say, look, this next guy is going to be 0, and then minus 10, minus 20, minus 30, minus 40. This is what the velocity does. It just, the acceleration causes it to lose 10 meters per second every second. Remember we said an acceleration can be written as 10 meters per second, right? And so in this interval, the average velocity is 15, because 20 plus 10 divided by 2 is 15, times 1 second is 15 meters. And so this would be 15 plus 60 is 75. Or I could add these two up and divide by 2. That would give me the average velocity of 25 meters per second. 40 plus 10 divided by 2 is 25, times 3 seconds is 75. So you can calculate it either way. So finally, in this interval, my average velocity is 5. I have initially 10, finally 0, so the average is 5. 5 times 1 second, 5 meters per second times 1 second is 5 meters, plus 75 is 80. Or I could say 40 plus 0 divided by 2 is 20, times 4 is 80. So the next one of these, this is going to be minus 5, because 10 plus minus 0 plus minus 10 is minus 10 divided by 2 is minus 5, and so this would be 75. I'd be subtracting, and if you work these out, you will notice so the object goes up and it comes back down, and at corresponding times it's at the same position. So on 1 second on either side of the highest point, it's at 75 meters. At 2 seconds on either side of the highest point, it's at 60, and then 35, and 0 back on the ground. Right. Notice we could use our other equations if we wanted to, because, for example, we could say, look, suppose we want to say at t equals, let's pick one, 6 seconds. We could grab equation 4, and we could say y equals y naught plus v naught y times time minus 1/2 g times time squared. This is the position, this is our equation 4 there, and we can calculate the height at this time given all these numbers. The initial height is 0, right? The initial velocity is 40 meters per second. The time is, what did we say, 6 seconds, minus 1/2. This is 10 meters per second squared times 6 seconds squared. And so this is 240 meters. That's what that one is, right? This is 6 squared is 36, times 10 is 360, divided by 2 is 180. I'm going to second square it here. It's going to cancel the second squares here, and so I get meters. Notice at 6 seconds, right? At 6 seconds, The height is 60 meters. Right. You can calculate these things in a variety of different ways with the various equations, and your answers will all be consistent. A ball is dropped off a bridge and takes 4 seconds to hit the water. And so here's my bridge, right? Here's my ball, right? And down here is the water. And so I'm going to call the initial height y0 and the final height y. And I'm going to say y is equal to 0, because I generally like to make the lowest point in the problem 0. A subtle point here is that if it's dropped off the bridge, here's me dropping something, right? v0 y is equal to 0 because it's dropped. It wasn't thrown downward, it was just dropped, right? And so I'm looking for, I know the time, I know the initial velocity, I know the final position. I'm looking for the initial position, and you might grab equation 4. And so equation 4 says, is this, and again, I'm picking this guy to be 0, and so I can subtract the y0 over, or I can say y0 is equal to minus v0 y times time plus 1/2 g times time squared, right? Because I just subtract these two guys over the other side. It gives this guy a negative sign and this guy a positive sign. v0 y is 0 because the thing's being dropped, and so y0 is equal to 1/2 g times time squared, which is 1/2 times 10 meters per second. Sorry, squared, times 4 seconds squared. And so the second squared and the second squared are going to cancel. 4 squared is 16 times 10 is 160 divided by 2 is 80. So y0 is the height of the bridge, is 80 meters. You could easily answer the question what was its final velocity. You're not allowed to say, anytime we're talking about projectiles, you have to talk about the velocity right before it hits. You can't say, well, it hits the water, it stops. You have to say, when you're talking about the final velocity, you're talking about the instant before it hits the water. It's not quite on the water. Just space there is almost 0. And so we can say Vy is equal to V0 y minus g times time. That was equation 2. We already said the initial velocity is 0. But we already knew this because we know that every second that goes by, the velocity changes by minus 10 meters per second. That's what gravity is, minus 10 meters per second per second. Since 4 seconds went by, it has to be minus 40 meters per second. Of course, in these free fall problems, we're neglecting things like air resistance. And other smaller factors. So a rock is thrown vertically at 20 meters per second, so upward, right? And so here's my bridge, here's my person, right? And it's thrown upward, V0 y equals 20 meters per second. Remember when we dropped it, it was going, there we go. It was going, its initial velocity was 0, right? Here's the here's the water down here. This is y equals 0. right? And they're asking us Vy equals question mark, right? And so here's a problem where we don't have the time. We have a distance and we have an initial and a velocity, and we're after a final velocity. And so you can look at equation 5, Vy squared is equal to V naught y squared minus 2g times y minus y naught. And so this is 20 meters per second squared minus 2 times 10 meters per second squared times its final position, which is 0 meters, minus 80 meters. $20 squared is 400, right? 10 times minus 80 is minus 800, times 2 is minus 1600, times a minus sign is 1600. So it's 400 meters squared per second squared plus 1600 meters squared per second squared, which is 2000 meters squared over second squared. That's my Vy squared. And so Vy is equal to the square root of that, which is about 45 meters per second. Now notice I'm taking the square root. Square roots can be plus or minus, and so technically I know it's going downward. And so Vy is minus 45 meters per second. An interesting note about this problem is that if this person had instead thrown it down at 20 meters per second, so instead of its initial velocity being plus 20 meters per second like it is here, if it was minus 20 meters per second, the answer wouldn't change, because that would still be squared, so the minus sign would go away, and I would still get a minus 45 here for my final velocity. And the reason, another way you can think of that is if he throws the ball up and then it comes back down, when it passes him again, just like we saw in the table earlier, the velocities at the corresponding heights are the same going up as they are coming down. And so when this goes up and comes back down, it's actually going, when it gets to here, at minus 20 meters per second. And so if you just throw it down at minus 20 meters per second, you're going to get the same answer. So we could ask the question, another question we can ask is, don't throw rocks off bridges. And so there are a lot of equations that would solve this. Since we know that our final velocity, Vy, is minus 45 meters per second, right, then I can say, look, I can use equation 2, and I can say Vy is equal to V naught y minus g times time, where time is equal to V naught y minus Vy over g, which is 20 meters per second minus negative 45 meters per second over 10 meters per second squared, which is about 6.5 seconds. So those are a few vertical motion problems.